Hello everyone, welcome to another video. And today in this video, we'll be solving this question, which is called convert a BST to a greater tree. And keep in mind that this is exactly similar to this question as well, also available on Leetcode, called binary search tree to greater sum tree, which is question number 1038. I'm not sure why there are two questions with the same logic, but understand that the same solution applies to both these questions. This is exactly similar to that question as well. So this is a medium level problem, which is very often being asked by Google, Microsoft, Adobe in their coding interview rounds, as well as in their online assessments. And if you like these kind of videos and consider them to be helpful, please do consider subscribing to the channel or like the video as well if you want, and share it with your friends or contact who are trying to prepare for interviews if you feel that this video is going to be helpful for them in their preparation, and that would mean a lot. So without wasting much time, let's quickly move on to the explanation of the question, what it says, and the most optimized approach, as well as writing its code. Okay, so the question says that given the root of a BST, we need to convert it to a greater tree such that every key, and key here refers to the value of a particular node. So every key of the original BST is changed to the original key plus sum of all the values greater than that particular key. Then they have just explained what a BST means. The left subtree values are smaller than the node and right values are greater, and both left and right subtrees are also BSTs. That's pretty obvious information. Then for example, in this particular test case, for node 7, the values which are greater than 7 are only 8. So we change it to 7 plus 8, which is 15. Similarly, for node 4, all these values are greater than 4. So 5 plus 6 plus 7 plus 8 plus 4, which becomes 30. Similarly, for node 1, we change it to the sum of all values which are greater than node 1. Basically, after 1, we have 2 and 3. And then these all values, which is the sum is 30, then plus 2 plus 3 plus 1, which becomes 36. Similarly, you need to update all the values and then return the root node of the updated tree. So they have also mentioned some other test cases. These are the values of a tree, and then these are the updated values. And then the constraints are that the number of nodes will be 10 raised to 4, less than that. And the nodes value can be negative as well, from negative to positive 10 raised to 4. And it will only have distinct values. And then the root is guaranteed to be a valid BST. So the property that the tree is a BST is going to be critical in arriving at the solution for this particular question. The optimized solution will involve the logic that the tree is a BST. Let's quickly move on to the explanation for the optimized solution. Alright, so let's move on to the explanation for this particular question. So for example, for this particular test case, this is the input tree that we have been given, and we need to convert this to this particular tree as the output tree. So this should get converted to this ideally, and this tree is what we want to return. So we'll be given the root node of the input tree, and after conversion, we need to return the root node of the converted tree. So as you can see, every node has values for nodes which are greater than that. For example, there's nothing greater than 8, so this remains as 8 only. Then for node 7, the only node greater than 7 in this tree is 8. So we add 7 plus 8 here in this particular node. So this becomes 15. Then similarly for 6, we add 6 plus 7 plus 8. So that becomes 21. Then for 5, we add all these values. So that becomes 26. And then similarly for all the values, you can see that we add all greater values to that value and update the node and then return the tree. So what should be the approach for this one? First is pretty simple. So for the brute force approach, what we can do is for every particular node, we'll iterate the tree once. So we'll iterate in whatever manner, either BFS or DFS. But then as you are iterating over all the nodes, so let's say you come to any particular node, let's say this node 6, then you need to update this node's value 6 to 6 plus the sum of all values greater than 6. So to do that, you can again iterate over all the values in the tree. So for example, for node 6, I'm going to again iterate over all the nodes starting from the beginning, and I'll keep on checking if that node is greater than 6. So we'll iterate for 4, it's not greater than 1, 0, 2, 3. None of them are greater. Then 5 is not greater. Then 7, we come to 7, which is greater. So we'll add 7 to the value of 6. Similarly, then we'll iterate over 8, and we find 8 is also greater than 6. So we'll add 8's value also to 6. And this is how we updated the value of this particular node 6. And we'll do this for every single node one by one. So you can clearly see that for every node, we are iterating over all the nodes once again. So for this one, the time is pretty obvious. It's going to be big O of n square, where n is the number of nodes that we have. And the space for this one, we are not actually using any auxiliary containers, so space will be constant for this one. But then there's a small optimization that you can do. Since we are given that this is a BST, not a normal binary tree. So for a BST, we know that the nodes which are greater will only lie towards our right subtree. So for 6, earlier we were iterating over all the nodes in the tree. We can do a slight optimization and iterate only over its right particular subtree. So for 6, we'll iterate over this much portion only. And then whatever the values of the nodes are, for example, 7 and 8, we'll keep on adding them to this particular value of 6. So 6 will become 6 plus 7 plus 8. And this is how we can make the change. In this one also, we are actually for every node, for example, for node 1, we'll be iterating over this particular subtree. Then similarly for node 4, we'll be iterating over this entire subtree once again. And then for 6, we iterate over this subtree. So you can see the repetitions, right? These nodes we are iterating over again and again. Then for 7, again, we'll be iterating over this node. So for every node, we are iterating over its entire right subtree, which will have repetitive nodes. So in this one also, we'll again have the time same as big O of n square only, and the space will again be constant. This is just a slight optimization over our naive brute force approach. But there's definitely a better way to do this. So let's discuss that. Okay, so let us now discuss the optimized approach for this one. So for the optimized approach, we need to make sure that we use the property that this is a BST that has been given to us. And so in a BST, we know that for any node, all values greater than that node will only lie towards its right subtree, and the smaller ones will lie towards its left subtree. And as you can clearly see, that's true for this tree. So how do we use this property? Basically, for every node, we need to change its value with all the greater nodes. So we need to change its value with all the nodes which are towards the right of that node. And for this one, clearly, for example, let's say once we update the value of 6, whatever value it gets updated to, which is going to be 6 plus 7 plus 8. So when we update the value of 5, we'll need to add these entire values to 5's value as well. So this clearly shows us that once we have something done for the right subtree, using that we can compute the values for the left one as well. So this kind of gives us a hint that we need to start from the right to the left, because we know that the maximum values in the tree are going to lie somewhere over here in the rightmost node, and the minimum ones will lie somewhere in the leftmost portion. So for the greatest values, we'll keep on adding the right ones, and then we'll keep on moving towards the left. And this clearly gives us an idea of not in order, but a reverse in-order reversal. So we know that an in-order reversal is basically the left subtree, and then the root node, and then the right subtree. But here what we are doing is first the right subtree. So for example, this one we'll update. This is the right subtree for this node. Then we'll update the root node using this value from the right subtree, and then we'll make a recursive call for our left subtree. So this is a simple reverse in-order reversal. And let's see how we'll do this. So in this one, of course, recursion will be used, and we'll try to do it in a single pass itself. So a single DFS call will do all the work for us. What we'll need for this one is a variable which keeps on storing the values for all the greater values for a node that we have found. What I'm saying is, for node 6, we'll have a variable which stores the sum of 6 plus 7 plus 8, which is the value which gets updated for this node. And the reason we need to store that value is because when we'll go to node 5, after, for example, this one is the right, then the root, and then the left subtree is 5. So when we call on the left subtree, which is node 5, we can simply use this sum 6 plus 7 plus 8 to add to this value 5. And that's it. We have updated this 5 node. Then the sum also gets updated. So sum will now be 5 plus 6 plus 7 plus 8. This is the sum that we'll be storing. And after this right subtree is done, when we come to this root value, we can simply use this sum to add to node 4, which will make the sum as 4 plus 5 plus 6 plus 7. And using that sum, we can keep on updating the values for the nodes in the left subtree as well. So let's say I have this variable that I've maintained called greater sum, whose value initially is 0. And this variable is going to be global, or you can also pass it by reference, which means this is going to be accessible in every single recursive call. This is not going to be local for one recursive function on top of the stack frame. So every recursive call will use the same value for the greater sum variable. And you'll quickly understand the reason for this. So the first thing we do is we use a reverse in order mechanism to traverse the tree. We'll first call on the right subtree, and then the root node, and then the left subtree. This is how we'll iterate. So the call for the root node, first we'll go to the right subtree, then again the right subtree, then again the right subtree. And when we reach this one, we'll find that the right subtree for this one is null. So as soon as we encounter a null node, we can simply return. We don't have to make any changes for that node. So we'll return back to node 8, which is a leaf node. Now for this node, we'll simply add the greater sum, whatever the value for the greater sum is right now, to this node's value. So this will be 8 plus 0, and we'll update this value. Once we update this value, we'll change the greater sum to this updated value. So this becomes 8, which is the updated value for this node. There's no changes to the leaf node, but once we do it for other nodes, you'll probably understand it. Then once we are done with the root, we make a call on the left subtree. So the left is again null. We'll return from the left, and then we return back to the root for this one. So once we come at this node 7, we'll again update its value to whatever its value currently is plus the greater sum. So this will become 7 plus 8, which is 15, and this value will get changed to 15. Now once we have changed this value, we again need to update the greater sum with whatever value we changed it to. So greater sum also becomes 15. Now we'll make a call on its left. There's nothing, null, so we'll return back. Then our control comes back to its parent, which is 6. So for node 6, again we'll add whatever the greater sum currently is. This will be 6 plus 15, which is 21. So this value gets changed to 21. And now we can again change our greater sum to this updated value, which is 21. Similarly, for 6, we'll make a call on the left now once the root is done. We'll come to node 5. For 5, again, we first iterate towards its right, it's null, we return. Now for 5, we update its value with whatever the greater sum currently is. So this will be 5 plus 21, which simply changes it to 26. This becomes 26. And now we can again update the greater sum to this new 26 value. Then we make a call to its left, it's null, we return. And then we come back to the parent of 6, which is node 4. So now for node 4, we will add the greater sum to this. So this will be 4 plus 26, which makes it 30. So this becomes 30. And so we can change the greater sum again to this node's value, which is 30. And now once this is done, we are going to make a call to its left subtree. So when we make a call to its left subtree, again the reverse in order mechanism is going to be followed. For this particular root node, we'll first go to its right, then again go to its right, and then again go to its right. This is null, so we'll return. Now we come to node 3. So for node 3, we can simply add the values 3 plus whatever the greater sum is, which is currently 30. So we add 3 plus 30, which makes it 33. So we are going to change this value to 33. Once the root is done, we'll call on its left, which is null, so we'll return back. And then the call moves to the parent. So for the parent node 2, we will again add greater sum value, and this greater sum would have become 33 now, the node's value. So to 2, we'll add the greater sum, which is 2 plus 33, which makes it 35. So this value will now become 35. And towards its left subtree, there's nothing, so we'll return back to the root. Then the call returns to the parent, which is 1. So for 1, we'll add the greater sum, which must have gotten updated to 35. So 1 plus 35 is what we'll get for this particular node, which makes it 36. So this value will now become 36, and the greater sum will also get updated to 36. So this is the sum value. Then once the root is done, we can return back to the left subtree, which is 0. For 0, again, we'll make a call to the right, which is null, and we'll return from the right. Then for the root, we can update its value, add the greater sum. So that is 0 plus 36, which again makes it 36. So this value becomes 36, and the greater sum also changes to the updated value, which is still going to be 36 only. After the root is done, we make a call to the left subtree. There's nothing, so we return. And once both the calls are made, the call returns back to the parent, which again returns back to the parent. And we come to the first recursive call that we made, the very first function call. And this has updated all the values. So once we are done, the recursion stops and the tree is now updated. So let's just see what the values for the updated tree right now are. Okay, so first we have the root node as 30. Let me just create it simultaneously. We have 30 as the root. Then towards its left, we have 36, and towards its right, we have 21. So that is 36 and 21. Then for 36, towards its left also we have 36, and right is 35. So this is something like this, 36 and then 35. Now towards the left of 36 there's nothing, but the right of 35 there is this node, which is 33. So the right side of 35 we have as 33. Then for node 21, towards its left we have this node 26, and towards its right we have this node 15. So this is something like 26 and 15. Now for node 15, its right is node 8. So this becomes something like this. This is the updated tree as the output that we are going to return back to the caller. So let's match this with the output that we were wanting. So 30, 36, 21, 30, 36, 21, then 36, 35, 26, 15, 36, 35, 26, 50, and 33 and 8. So as you can see, they clearly match both these trees, and we have in place changed it to a greater sum tree. So the time for this one, we are only making one DFS recursive call and iterating only once over all the nodes and updating the values. So clearly we are only iterating over every node a single time. So if there are n nodes, so the time will be big O of n. And then to talk about the space, so what we are doing here is not making any auxiliary containers, but we are simply using one global variable, which is called greater sum, which is accessible to every recursive call. So greater sum is again constant in terms of space. So this is big O of 1 for the space. So big O of n time and big O of 1 space. This is the most optimized approach for this particular question. And this approach is possible only because this is a BST. For any normal binary tree, this would give a wrong result. This would not be possible. But since they have mentioned it to be a binary search tree, we are using that property to get it done in a linear time. So this was all about the explanation for this question. Let's quickly move on to writing the code for this one, which is now going to be pretty simple once you understood how it's being done and how the recursive calls are being made. Okay, so let's move on to writing the code for this one now. The optimized approach will code it up. So we have a function called convert_BST, which accepts the root node of the tree of the BST. And then we also need to return the root node of the updated tree. So every node should have values which are greater than that node added to its value. So as we discussed, we'll need a helper recursive function for this one. So we'll have another function for this one called a helper function. And this is going to be the recursive function which we'll use. And the reason this is void is because this function, we don't want to return anything from this. This is only going to be used to update the values of my original tree. So once we call this function, we are going to assume that all the values have been updated. So this will again accept the root node of my tree. Let's call it root only. And then as we discussed, this should also accept an integer variable called the greater sum, which will be common to all the recursive calls. So that's why I'm passing this value with reference. So let's call it greater sum. And before I make a call on this, let me just create the value greater sum inside this function. So we'll initialize this value with 0 because currently the sum is 0. Basically for the rightmost node of the tree, we don't have to add any value to that node. And then after that, I can simply make a call on this particular function, passing it the root node as well as this value, the greater sum value. So it's currently 0, and that's what I'm going to pass to this function. So once we are done with this particular call, I'm going to assume that all the values have now been updated in place. So this root node will now point to the updated tree. I can simply return the same root node from here as well. So all we need to do is implement the logic for our recursive call. The first thing we need to keep in mind as we discussed is if we reach a null node, so if my root is null, so I can simply return from this function. I don't need to make any recursive calls. And otherwise, if we have a particular node, so the first thing is we need to make a call on the right subtree. As we discussed, we are going to traverse in reverse in order fashion. So that is how we are going to traverse the tree. So the first thing is I'll make a call on the right subtree. So I'll call on the right node of my root node, passing it the same greater sum function, greater sum variable, sorry. So basically this statement will update all values in right subtree. So after this, I can safely assume that all my values in the right subtree have been updated to their greater sum values. So once I'm done with my right subtree, all I need to do is change the values for my current root node. So for that, as we discussed, first we'll change my current root node's value. Basically, I can simply update the value of my current root node with whatever it is, and to that we'll add the value of the greatest sum. So this must be storing the sum of all the values which are greater than my current root node. So this statement simply updates the current root node value, and then once I'm done with updating this value, I can simply update my greatest sum to whatever my root node's value now is. So the updated root node value is going to be my updated greatest sum as well, because after this I'll be iterating towards the left subtree. For those values of my left subtree, this value needs to again be updated to the right one. So now I can simply make a call to the left subtree. So root left, and then the greatest sum remains as it is, which is now already updated. So once I'm done with this call, this is going to update all values in left subtree. So this is going to be the last function that we call, and you can see that this is tail recursive. And once I'm done with calling this particular function, my helper function must have updated all the values. So since I'm calling this here, I can simply return the updated root from this particular function. So I think that's all that I need to take care of. So if I run this now, this should work for all the test cases, and it's working for the sample test cases. And if I submit this, this should be getting accepted as well. And yeah, this gets accepted and it's faster than 82%. So it's a pretty good solution for this question, the most optimized one. And this is being done in linear time in constant space. That was it for the optimized solution of this particular question. I hope you understood the explanation, and if you have any doubts, put them down in the comment section below. And do share it around, subscribe to the channel for more content related to computer science, software engineering, tech, coding, and productivity tips. And you may give the video a like if you appreciate these efforts. And for any other questions that you have that you would want me to solve, let me know of those particular questions. I'll make videos on the solutions of those questions as well. And that's it for now. Thank you so much for watching this video, and I'll see you very soon in the next one.